Hello, this is our presentation for our independent research project. Our project was more of an engineering design project and based on creating a thermoelectric flashlight.
So the question we wanted to answer with this project was if it was possible to construct a functioning flashlight that was only powered by the heat given off by the human body and whether or not temperature would affect its performance. And so our hypothesis was based on background information we read about like the Seebeck effect, and our hypothesis was basically that like the colder the water inside of the flashlight was, the more energy it would produce.
And the purpose of our project was to try and investigate more into one avenue of renewable energy, which in this case was obviously thermoelectric power. We wanted to create a flashlight which could be powered on the fly while hopefully not sacrificing the functionality of a regular flashlight.
All right, so for in terms of background info, we did a lot of research about like how uh, ever since the Industrial Revolution, there's been a lot of progress in the ways humans harness energy, and so a lot of that has come through both finding cheaper sources of energy as well as more renewable sources of energy. But while it used to be like much more important to find like a cheap source of energy, as we are starting to realize like that this planet's resources are dwindling in the form of like fossil fuels and stuff, renewable sources of energy are becoming more of like an important thing that we need to focus on. And so that's why we wanted to create this project, because it's powered solely by renewable energy.
Yeah, and so most of what this project is powered on is like kind of all backed on the Seebeck effect, which is pretty much a principle that like a temperature differential between two different conductors or semiconductors causes a flow of heated electrons to travel towards the cooler side. By harnessing the electrical energy created by this effect using Peltier tiles and amplifying the electricity produced with a voltage amplifier, it is possible to use thermoelectric energy as a power source to many things. And from left to right here, you kind of see diagrams of a very simple um, implication of the Seebeck effect to the most complicated, which is actually the Peltier ties that we use to produce energy in our project. And you see on the left, it's very simple. Then in the middle, it's a little bit more detailed with the electrons and protons. And then on the right, it is what it actually looks like in physicality with the electricity. So for our materials and tools, one of our main tools was a soldering iron. For all the wiring connecting the LEDs to the Peltier tie wires and like soldering all the Peltier ties to the sides of the device, we needed to obviously use that. And then the wires, clippers, and strippers to get more of the wire exposed from the rubber, those were very helpful. And the handsaw we used in shaping the PVC tube as well as the head of the flashlight, and the hydraulic saw was used to cut most of the PVC and the aluminum. And the brush was also used to apply epoxy.
All right, so in terms of procedure, I don't want to fully explain it just because that would take too long. But the first half was mainly just doing construction of the PVC tube using things like hand saws and whatnot to cut off cross sections that would make it like appropriate to attach like the heatsink and Peltier tiles. And for that, we used like the hydraulic saw, like Dylan said, and the hand saw. And yeah.
And the second half of building and testing the flashlight was more so wiring and making sure that it was all waterproof and that nothing was really leaking. And so after we wired everything up and secured the water in the body, we were all good for that.
And so this is the data that we gathered when we were testing our project. As you can see in the bottom right graph, as well as the top left table, the colder that the water was, the more lumens of light were produced by the flashlight. In every single one of our tests, it remained relatively consistent, as well as the fact that the boiling hot, or not boiling hot, but very hot water, the flashlight didn't work at all because there was not a high enough temperature differential.
And so in conclusion, the results of this experiment confirmed our suspicions that the performance of the flashlight was determined by the heat differential between the aluminum heatsink and the temperature of the user's hand. As the temperature differential increased, the number of lumens produced by the LED also increased. There were some room for improvement in our designs, but ultimately we accomplished our goal and it tested well, and that's what mattered.
How does carbon dioxide released into the environment have a detrimental impact on calcium carbonate shell formation? By Lily Raymond and Priya Cooper.
Purpose. The goal of the experiment is to see how the rising levels of acidity in the ocean affect organisms with calcium carbonate shells in the ocean. The hypothesis states that the greater the amount of hydrochloric acid, the greater the amount of carbon dioxide produced, and the greater the difference in mass of the calcium carbonate shells. Through the experiment, ocean acidification was replicated through the use of hydrochloric acid. The experiment's data shows that an increase in CO2 in seawater does have a detrimental impact on marine life with calcium carbonate shells. The hypothesis is justified by the experiment.
Our hypothesis was that the greater the amount of hydrochloric acid, the greater amount of carbon dioxide produced, and the greater the difference in mass of the calcium carbonate shells.
Background information. Ocean acidification is the increase in the ocean's acidity as a result of CO2 produced by humans. The equation CO2 plus H2O equals H2CO3 equals 2HCO3 plus H represents this process. The CO2 in the air is increasing from burning more fossil fuels. The ocean absorbs 25% of CO2 in the air and has become 30% more acidic in the past 200 years, the fastest change recorded. Organisms with calcium carbonate shells are at risk of becoming extinct. Larvae are at most risk because of their microscopic shells. Carbonic acid releases hydrogen ions, acidifying the ocean. Also, carbonate ions, a mineral that builds shells, bond with hydrogen ions to form bicarbonate ions, which are useless in building calcium carbonate exoskeletons. The average pH level of the ocean is about 8.1. If the pH were to fall slightly, the shellfish and coral populations of the ocean would plummet. 25% of marine life live in coral reefs, so the ocean's ecosystems will be in chaos. 3.2 billion people rely on fish as an essential part of their diet, so almost half of the world's population would face starvation. For example, the important indigenous crab shells are dissolving, straining coastal communities.
Some of the materials we used in our experiment was ocean water, plastic containers, calcium carbonate shells, a mortar and pestle, 2 trays, 3 beakers, 2 graduated cylinders, hydrochloric acid, a rubber stopper, a graduated cylinder with a clamp, a funnel, pH paper, and some filter paper.
Methods. We crushed 3 grams of calcium carbonate shells with mortar and pestle, and we poured that into a small tray to record the mass, and we poured that into a beaker. Then we measured 20 milliliters of ocean water with a graduated cylinder and poured that into the beaker too. Then we measured different amounts of hydrochloric acid for each trial 3 times and poured that into the beaker. We measured 0, 1, 1.5, 2, and 3 milliliters. Then we quickly, after adding that, we quickly plugged the beaker with a rubber stopper and graduated cylinder with a clamp. Then we wrote down our observations for 2 minutes, and then after those 2 minutes, we recorded the CO2 in a graduated cylinder. We then removed this rubber stopper and graduated cylinder with a clamp, and then we filtered the pieces of shell through filter paper in a funnel. Then we removed the pieces of shell from filter paper to dry on paper towel, and then we transferred the piece of shell to a small tray to measure the mass.
This is a picture of our experiment. Next is the data portion of our presentation. Table 1 is the difference in weight before and after the reaction. The average for trial 1 was 3 grams, the average for trial 2 was 2.30 grams, trial 3 was 2.31 grams, trial 4 was 2.42 grams, and trial 5 was 2.06 grams.
Table 2, the relationship between hydrochloric acid and CO2. The average for trial 1 was 0 milliliters, the average for trial 2 was 8.6, the average for trial 3 was 48, the average for trial 4 was 74, and the average for trial 5 was 113.
Figure 1 shows the relationship between the amount of hydrochloric acid and the mass of the shell after the reaction. When hydrochloric acid was added into the solution, the mass of the calcium carbonate shells decreases.
Figure 2 shows the relationship between the amount of hydrochloric acid and the amount of carbon dioxide. As the amount of hydrochloric acid in the solution increases, the amount of carbon dioxide released from the reaction increases.
Figure 3 shows the relationship between the amount of hydrochloric acid and the amount of carbon dioxide. As the amount of hydrochloric acid in the solution increased, the amount of carbon dioxide released from the reaction increased.
Conclusion. The results of the experiment partially support the hypothesis. Increasing the amount of hydrochloric acid in the solution increased the amount of CO2 produced from the reaction. There was an exception in the hypothesis. It was expected that the mass change of the shells before and after the reaction would gradually increase. The mass changes for each trial are either similar or disproportionate, though. The data was accurate, but it was not precise for several reasons. Petroleum jelly had to be applied to the graduated cylinder so it could fill up with CO2 easily. The rubber stopper had to be placed on top of the beaker after adding hydrochloric acid. The shell also had to be transferred from the filter to the tray. The experiment is related to the real world because ocean acidification is a pressing issue that affects everyone.
Some of the highlights of this project were going to the beach to collect shells, water, and other materials necessary for the project, crushing the shells up for the experiment, watching the reaction take place in each trial, and making the poster board for the final project.
Obstacles we faced were the rubber stopper requiring petroleum jelly to be applied to it so the measurement of carbon dioxide produced and the reaction could be recorded precisely. The graduated cylinder had to be placed on top of the flask quickly after the hydrochloric acid was added to the mixture of crushed shell and ocean water, or else the carbon dioxide being produced from the reaction would escape before the clamp was in position. The shells also had to be dried after being weighed after the reaction. However, any leftover water on the shells that may not have been dried could have also affected the change in mass measured after each trial throughout the experiment.
This is our works cited page, which shows some of the sources that we used throughout this project, and that concludes our presentation.
Our experimental question was, how does a type of alcohol affect the rate of combustion?
Our hypothesis is an increased amount of hydrogen and carbon atoms in the compounds increases the rate of combustion.
The background information, we tested methanol, ethanol, and isopropyl alcohol, and carbon and hydrogen are found in flammable materials. During a reaction, the oxygen from the air reacts with the carbon and hydrogen atoms to form carbon dioxide, water, and other gases. When heat is added to the alcohol using a lighter, the energy from the heat causes the carbon and hydrogen atoms to break their bonds with the compounds and to form new molecules. And all three of these alcohols contain the same three elements, carbon, hydrogen, and oxygen. For each type of alcohol, one molecule contains one oxygen atom. However, the number of carbon atoms and hydrogen atoms differ between the three types of alcohol. So we were wondering if this was if the change in the hydrogen and carbon atoms causes the different rates of combustion.
Our materials are methanol, ethanol, isopropyl alcohol, a lighter, a timer on our phone, a graduated cylinder, a pipette, and an evaporating dish. And our procedure was to measure 2 milliliters of alcohol in a graduated cylinder, pour all the alcohol into a petri dish, use a lighter to light the alcohol in the petri dish until it begins to burn, and use a timer to time how long the alcohol burns for. And we had to begin the timer from when the alcohol first lit and end it when the flame goes out. And we repeated these steps for all the alcohols.
The equation was, for methanol, it was 2CH4O plus 3O2 molecules is 2CO2 and 4H2O molecules. Ethanol, it was C2H6O plus 3O2 molecules is 2CO2 and 3H2O molecules. And for isopropyl alcohol, it was 2C3H8O plus 9O2 molecules becomes 6 CO2 and 8 H2O molecules.
The independent variable is the type of alcohol, so methanol, ethanol, and isopropyl alcohol. The dependent variable is the time for combustion. The control is the amount of alcohol, 2 milliliters. And the constant is the surrounding environment where the experiment takes place, the constant temperature, humidity, and amount of energy added to the system.
These are the results for isopropyl alcohol. We did 15 trials, and the average combustion length was 1 minute and 41 seconds.
These are the results for the ethanol. We also did 15 trials, and the average length of combustion was 2 minutes and 1.24 seconds.
And for methanol, we did only 5 trials because the times are more consistent. The average length of combustion was 1 minute, 32 seconds.
So for our calculations, the alcohols used in the experiment had different concentrations. The isopropyl alcohol had a concentration of 70%, ethanol had a concentration of 95%, and methanol had a concentration of 100%. In order to compare the alcohols accurately, a mathematical equation was written to find the number of seconds it took 0.1 milliliters of 100% concentration of isopropyl and ethanol alcohols to be burned.
So these were the results after the calculations had been done, and it shows the average rate of combustion in seconds for each of the alcohols.
So in conclusion, when the final figures are compared after the calculations, the hypothesis is proven correct. Isopropyl alcohol burned the longest with an average time of 2.25.39 seconds. Ethanol burned the longest time, or the second longest time, with a time of 2.07.62 seconds. And methanol burned the shortest amount of time with an average of 1.32.46. And it contained the least amount of carbon and hydrogen atoms.
So some random errors that could account for errors. For isopropyl alcohol and ethanol, each group of 5 trials were conducted on different days, so the current day's conditions could play a role in the combustion reaction, such as the room temperature, and some systematic errors could be the variation of time.
Hi, I'm Isabel.
And I'm Hannah.
And we investigated how different concentrations of hydrochloric acid affect the mass of calcium carbonate shells.
Concentration of carbon dioxide in the atmosphere has increased by 30%, and 25% of the CO2 in the atmosphere is absorbed by the ocean. The ocean has absorbed about 525 billion tons of CO2 from the atmosphere, or around 22 million tons per day. This has various negative effects on the many organisms who call the ocean their home.
So specifically, organisms like oysters, clams, snails, urchins, and corals that have exoskeletons made up of 98% calcium carbonate, or CaCO3. Oysters filter about 25 to 50 gallons of water a day. Corals provide habitats for over 9 million different species, and other organisms are simply an important part of the food chain. So when CO2 dissolves in water, carbonic acid is created, which increases the ocean's acidity, and this ocean breaks down calcium carbonate shells and directly interferes with their ability to build new shells, as hydrogen ions bond with their building blocks and create bicarbonate, which is useless to them. Oh, and these effects will take years, but we turn to science to see how aggressive the reaction between acid and calcium carbonate is, to see how big the problem we are faced with is.
So our hypothesis was that at the highest concentration, it will take no more than 2 minutes to see at least 40% of the mass gone from various shells. Our independent variable was the concentration of hydrochloric acid in moles per liter, and our dependent variable was the mass of the shells in grams. So to carry out our experiment, we used these materials to, we used these materials. So basically, we started out with 3 beakers in a fume hood labeled 6, 3, and 1 HCl. So we poured 50 milliliters of water into the first beaker and then added the 50 milliliters of the hydrochloric acid and stirred with a glass stir, which created a new concentration of 6 moles per liter. And we basically repeated this with the previous concentration of each acid until we were left with 3 different concentrations of 6, 3, and 1. In regards to the shells, we crushed shells using a mortar and pestle, and we measured out 15 trays of 2 grams each. And to kind of give that mimic of a wave in the ocean, we used a magnetic stir to stir the acid and the crushed shells with 5 trials each for each concentration of acid, and we let them dry out overnight or over a couple of days, whatever it took to make them completely dry, and measured and recorded the mass lost.
So these graphs here show the mass that was lost with each molar concentration, and our original table had 5 trials each, but it was too big and didn't fit in the presentation, so I took the average of all of them, and as you can see, with the molar concentration of 6, 88.4% was lost, with 3, 78.5, and with 1, 59.6, and this is a graph that shows the table. And then we have this picture which shows the shells before and after. The top is before and the bottom is after. This is what the shells looked like only after 2 minutes.
So the purpose of our experiment was to determine how much mass calcium carbonate shells lose when exposed to different concentrations of hydrochloric acid. And our results did support our hypothesis to an extent. The hydrochloric acid with a concentration of 6 moles per liter did cause the most mass change. However, the strength of high concentrations of acid is underestimated. The concentration of the 6 mole per liter acid produces an average 89% mass loss as shown in the chart, and the lowest tested produces an average 60%. Which means that even acids with a lower molar concentration can quickly break down carbonate shells. There could be errors to cause the data to vary. Some shells could get caught in the filter, leading to an inaccurate measurement of the mass. So to avoid this, we scraped the shells off of the filter very carefully to ensure that there was nothing left, even the tiniest pieces. And basically, in conclusion, the results of this experiment strongly prove that acid is detrimental to organisms with calcium carbonate shells. And if organisms cannot produce their shells and their larvae cannot survive, the marine ecosystem will be drastically thrown off balance and the effects will become very clear. Humans must be mindful of their carbon emissions to prevent this from happening.
Thanks for watching.
Thanks for watching.
So our essential question was, which liquid antacid works best at neutralizing stomach acid? This will be determined by the amount of antacid drops that were added to each tube.
Our purpose of the experiment was to discover which liquid antacid neutralizes stomach acid the fastest, and our hypothesis was that the antacid with the most basic contents would take the least drops to neutralize our mock stomach acid solution.
For our background information, we decided to research antacids. We discovered that many people suffer from common problems that antacids can solve, such as nausea, heartburn, and abdominal pain. Antacids are weak bases that function as a way to raise gastric pH to neutralize stomach acid, and this relieves many of these common pains.
So for our materials and methods, the first step was preparing the tubes. We had 5 test tubes placed in a holder, each labeled with an abbreviation based on the antacid they would contain. G for Gaviscon, as an example. We also had Maalox, Mylanta, and Pepto-Bismol. The 5th test tube was left blank because it was our control for the project. Next, using a pipette, we added 10 drops of grape juice, no sugar added, to each tube, including the control. Afterwards, we also added 10 drops of lemon juice to each tube, and this mixture simulated stomach acid for our experiment to take place in.
After adding the stomach acid, the corresponding antacid was added to each tube 1 drop at a time in separate clean pipettes until the solution changed color. Some examples of these colors are light pink, opaque pink, bubbly pink, or dark pink. These new colors differed from the light clear color of the control, and this signified neutralization. After seeing a color change in each tube, the dropping was stopped. We held the control tube next to each particular tube being tested to observe the most accurate color change possible.
Finally, for recording the results, the number of drops required to neutralize each antacid were recorded in a table per trial. Along with the number of drops, we also recorded the color of each neutralized test tube compared to the control. And after recording the results, the amount of drops of each antacid required to neutralize our mock stomach acid solution were averaged for more accurate and clear data.
To display our data, we decided to show a graph. This graph shows the average number of drops needed to neutralize the mock stomach acid solution for each antacid over the course of 4 trials. The color bars for each antacid display the color observed after the neutralization.
We also created a table which also displays the average amount of drops needed to neutralize our stomach acid solution over the course of 4 trials, along with the average amount of drops for each antacid per trial. The average color change is also displayed above the average.
So for our conclusion, the hypothesis of this experiment is mainly supported by the results that were recorded. The antacid with the most basic content neutralized stomach acid the fastest to some extent. Maalox neutralized the stomach acid the fastest with an average of 4 drops. Mylanta had an average of 5 drops. Pepto-Bismol, although differing in composition, had an average of 6 drops. Gaviscon had an average of 7.75 drops.
Our hypothesis was proved to be partially correct, considering the fact that the most basic solution was the antacid with the most consistent results. A higher quantity of aluminum hydroxide, also an antacid, is present in Mylanta, making it the most basic antacid. We proposed that if aluminum hydroxide was included in larger quantities than the other antacids, those bases may have had a more rapid neutralization rate. Out of the 5 trials, the last 4 had similar numbers, as mentioned before. Many errors were committed in the first trial, so we decided to disregard it from the information displayed in the graph. But throughout the experiment, each specific antacid had a similar neutralization rate.
For our highlights and obstacles, our highlights were that our data was very conclusive for the most part, and our experiment came together very well. We really enjoyed our experiment and found the procedure very manageable. Our experiment in the labs and chemistry class helped us create a successful and clear procedure to follow. Our obstacles were that an error may have been committed along the way to skew the results of Malox to be lower than they are in actuality. The results in our experiment were fairly precise. However, the results from Pepto-Bismol differed from the others, as it did not contain perceptible amounts of aluminum hydroxide, therefore making it a different antacid. This was learned after examining the contents of each antacid following the experiment's conclusion.
And that just about does it for our experiment. Thanks for watching!
Will be the most effective ice melt. This prediction can be justified by the fact that it has the most ions, meaning the highest ability to split apart the water molecules to melt the ice.
So materials and methods are materials: water, iodized table salt, potassium chloride, magnesium chloride, 4 beakers, a measuring spoon, and a scale to measure mass.
Okay, and then for our measurements, the ice cubes were measured to be 20 milliliters of water by a graduated cylinder, and then each was frozen in identical mold. So there's the same surface area, so it's spread evenly and it's accurate that way. And then we zeroed the scale with a watch glass and then added 5 grams of each salt and then labeled them. And then we also did a control. And then we took each ice cube out of the freezer one at a time to make sure that there was no melting like outside of the time trials.
Setting up. To prevent melting before the start of the experiment, ice cubes were taken out of the freezer one at a time and placed on a larger watch glass. A plastic spoon was used to spread and place the salt as to not interfere with any chemical properties of the salt like a metal spoon could. It was important to label each ice cube to be sure that each measurement and calculation was precise.
So for our trials, we had a stopwatch on an app called Timer Plus, that was labeled for each type of salt and like which trial it was. And we did 5 trials with 3 salts and 1 control. And then once the ice was completely liquid, that's when we stopped the stopwatch, and then we recorded the data in a table. And then the table also had the Van't Hoff factor, which is the number of ions like per element, the freezing point depression constant, the time it took to melt, and the formula for each type of salt, and all that.
Calculations. The freezing point depression formula was used to calculate the final temperature of the ice after the salt had been applied, which is the new freezing point of each ice cube. So first, the molality of the solute was calculated by mass of solvent divided by molecular weight times kilograms of the solvent. The molar freezing point constant with the Van't Hoff factor, which depends on the type of salt. The salt that was plugged into this formula and had the lowest number was the salt that worked the best for melting ice because it indicated the lowest freezing point.
So then we have this figure that shows the graph of the freezing point depression colligative, and it signifies the standard freezing point of water. And then this one shows what happens to the freezing point depression graph when the standard freezing point is lowered. The black dashed line shows how the purple and blue lines expand as the freezing point is altered.
And then this is our data. So this bar graph shows the average melting times of each salt, and it shows that magnesium chloride had the lowest average melting time, which meant that it was the best salt for ice.
And then this was our table, which had like the freezing point depression for each one. And magnesium chloride, like it didn't have the lowest freezing point, but it had like it was consistent over time.
Okay, so our conclusion was that Magnesium chloride is the most effective salt because it's the highest number of ions, 3, which is vitally important when melting ice. This is proven by the average melting times, where magnesium chloride has the lowest melting time, and its freezing point depression is also lowest. So highlights: recording the data for each ice cube, and obstacles: applying the data to the formula, measuring the correct amount of water.